All right, let's build something together. And I'm not talking about hammers and wrenches, I'm talking about math. We're going to uncover the special language physicists had to invent to describe all the invisible forces that shape our universe, everything from magnetism to light itself.
But seriously, think about that for a second. How would you actually map something you can't see? Like the magnetic field that protects the Earth, or the Wi-Fi signal traveling from your router to your phone. I mean, these things are totally real. They have a shape and a direction, but they're completely invisible. So where do you even start? Well, the answer is this really beautiful and powerful framework called vector analysis. You can think of it as the language we use to give shape and form and substance to all the unseen forces around us. And right now, we're going to learn its basic alphabet and grammar.
Okay, so every language needs to start with some basic words. And in the language of fields, our most fundamental word is actually a concept you've probably heard of before. First, we have to draw a line between two different kinds of quantities. On one side, you have scalars. They're easy. They're just numbers. The temperature is 72 degrees. That's all the information you need. But on the other side, you have vectors. And a vector has a number, a magnitude, but it also has a direction. It's not enough to say the wind is blowing at 15 miles per hour. You have to know which way it's blowing. North? South? That direction is crucial. So, the vector, that's our key building block. It's got a size, what physicists call magnitude, and it's got a direction. And honestly, the easiest way to picture one is just as an arrow. The length of the arrow tells you how big it is, and the way it points tells you its direction. Simple as that. This arrow is our basic word. Okay, so we have our words, these arrows. Now we need some grammar. We need rules for how to combine them to say something meaningful. So let's look at two fundamental ways we can multiply these vectors together.
First up is something called the dot product. Now, what's interesting here is that this operation doesn't give you another arrow. It just spits out a single number, a scalar. And what that number tells you is really simple. How much are these two vectors lined up with each other? It's basically an alignment check.
This diagram shows the idea perfectly. To get the dot product of A and B, just imagine shining a flashlight straight down onto vector A. The key part is the shadow that vector B casts onto A. You're basically multiplying the length of A by the length of that shadow. So if they're pointing the exact same way, you get a big shadow and a big dot product. If they're at a right angle to each other, no shadow at all. The dot product is just 0. All right, our second grammar rule is the cross product. And this one, well, it's a bit of a magic trick. Because when you cross two vectors, you don't get a number. You get a whole new vector. And here's the wild part. This new vector points in a direction that's perpendicular to both of the vectors you started with. Just look at this diagram. If vectors A and B are lying flat on the page, their cross product, this n hat vector, points straight up, right out of the page. It's like you're conjuring up a third dimension from the flat two-dimensional surface you started on. It's really wild stuff. So this might make you wonder, with regular old numbers, the order you multiply things in doesn't matter, right? 2 times 3 times 4 is the same as 4 times 3 times 2. We all learn that. But does that same intuition hold up here with the cross product? Can we just jumble the order around? And the answer is a big, fat no. When it comes to the cross product, the order is everything. You can easily have a situation, like the one from problem 1.2, where grouping the vectors one way gives you an answer of 0, but grouping them a different way gives you, well, something else entirely. So this is a whole new ballgame with a whole new set of rules.
Okay, so we've got our words and our grammar. Now let's bring in the big guns. We're going to mix in a little bit of calculus to create our master tools, the things that are finally going to let us see the shape of these invisible fields.
Our first master tool is called divergence. And the best way to get it is to just imagine our vector field is the flow of water. Divergence lets us go to any single point in that water and ask a simple question. Is this spot a source, like a faucet gushing water out, or is it a sink, like a drain pulling water in?
Right, so is it a source or a sink? If you calculate the divergence and get a positive number, you've found a source. Water is flowing out. If you get a negative number, you've found a sink. Water is flowing in. And if the divergence is 0, it just means whatever flows into that point flows right back out.
Okay, on to our second master tool, curl. So if divergence is all about stuff flowing out or in,
Curl is all about whether stuff is spinning. It's a precise measure of the swirl or the circulation in a field right at one specific point. Now, take a look at this whirlpool-like field here. The absolute best way to understand curl is to imagine dropping a tiny, tiny little paddle wheel anywhere in this flow. The curl tells you exactly how fast and in what direction that little paddle wheel would start to spin. It's a perfect, direct measure of the local rotation in the field. So here's the main takeaway. It's actually incredibly elegant. With just these two tools, we can characterize the geometry of any invisible field. We just go to a point and ask two simple questions. 1, is this a source or a sink? That's divergence. And 2, is there any rotation here? That's curl. From those two answers, we can build a complete picture of the whole field. So there you have it. We've assembled our toolkit. We have vectors, we have dot products and cross products, and we have divergence and curl. This whole system, this is the language of fields. So the big question is, what can we do with it? And the answer is just staggering. I mean, this isn't just a math game. This is the absolute bedrock of all electricity and magnetism. It allows us to perfectly describe the fields coming off of static charges, to map the forces inside of magnets. And this is the most beautiful part, to unify them into a single theory of electrodynamics, a theory that reveals that light itself is just a wave traveling through these very fields. And you might be thinking, okay, cool for physicists, but what does this have to do with me? Well, here's why it matters. This isn't just some abstract exercise. The equations that govern your Wi-Fi signal, that make your cell phone work, that run the entire power grid that's lighting up your room right now, they are all written in this language of vector analysis. It's the hidden operating system running our modern world. Think about that for a second. By inventing a language to talk about something nobody could see, we unlocked the secrets of electromagnetism and literally built the world we live in today. And that leaves you with one final big question. This toolkit revealed an entire invisible world. What other hidden universes are still out there, just waiting for us to find the right words, the right language, to finally see them?